In this work, we present list, learning implicitly from spatial transformers for single-view 3D reconstruction. Recovering the 3D surface from 2D image has been a long-standing objective in the field of computer vision and image processing. It has numerous applications in various fields, including computer graphics, augmented and virtual reality, robotics, and medical imaging. Photogrammetry is one of the prominent techniques for 2D to 3D reconstruction. However, 3D reconstruction via photogrammetry requires multiple images of the same target, which is difficult to achieve sometimes. With the advancement in RGB camera, now there exists a vast number of images without any matching pair. An accurate recovery of 3D surface from these images could potentially provide us with a low-cost source of realistic 3D data. Current techniques in this realm rely on camera parameters to extract local features from the image, which are difficult to get for real-world images. To overcome this shortcoming, we introduce LIST, a novel deep learning framework that reconstructs the topological and geometric structure of a 3D object from a single image. This does not depend on weak perspective projection or camera parameters for training or inference, and shows superior performance against the state of the art on both synthetic and real-world datasets. Here is an overview of LIST. In the following slides, I will explain each component of LIST in detail. To recover a 3D object, LIST requires a single image and Curie points collected from a 3D unit cube. First, we utilize a pretend CNN to collect features from the input image. From the collected features, we predict a coarse point cloud shape of the target. To account for the imperfection in coarse prediction, the predicted coarse shape is then converted to a probabilistic occupancy grid via a shallow neural network. Next, we encode the occupancy grid with a 3D encoder and collect multi-scale features at every Curie location. Research have shown that only global image features are not sufficient to faithfully recover the geometric details of the target. In their attempt to collect local features, current works rely on camera parameters in training and employ a separate pose estimation module during inference. In contrast, we utilize the spatial relationship between the coarse shape and the input image. Since the input image is a spatially transformed view of the predicted coarse shape, we utilize a spatial transformer to predict the transformation and localize the Curie point in input view. Note that the spatial transformer does not require any camera parameter and can be optimized directly with LIST. Next, we query the local image features with the localized Curie points and fuse them together with the multiscale 3D features to predict a sign distance field at each Curie location. Finally, we utilize the matching cube algorithm to recover the 3D surface from the sign distance prediction. We optimize LIST by combining three loss functions. The coarse prediction is optimized by minimizing a chamfer distance. The occupancy prediction is optimized by minimizing the binary cross entropy. The SDA prediction was optimized through mean squared error. LIST shows superior performance than current works in reconstructing 3D from synthetic data such as ShapeNet. Quantitatively, LIST outperforms the current arts in almost all cases. Qualitatively, LIST shows superiority in recovering intricate geometric details than current arts. Furthermore, LIST can resolve structural ambiguity introduced by the input view direction and recover better geometric details. In addition, LIST maintains geometric consistency between different views of the same object and shows superiority in recovering occluded surface. An evaluation of the isolated occluded surface shows LIST can outperform current baselines by large margin. Finally, LIST shows superiority in recovering 3D surface from real-world images. Compared to current works, LIST can recover much better intricate geometric details. To summarize, in this work we introduced LIST, a new deep learning framework that reconstructs the topological and geometric structure of a 3D object from a single image. We have designed a novel technique to collect local features from the input image without relying on camera parameters or weak perspective projections. We achieved superior performance in single-view 3D reconstruction on both synthetic and real-world dataset. Thank you for your attention. Please visit our GitHub page for more details about LIST.